All right, we've started a new chapter in the textbook that we're following, and this chapter is on linear transformations. And so if you'll remember when I was talking about matrices being maps or functions, basically we were looking at transformations, right? Because it was taking Euclidean space of dimension n and mapping it to Euclidean space of dimension m, say, right? And so just kind of a recollection of what what I was talking about there, what like when I was looking at like kernel and image and things like that, right? I was kind of teasing what we're talking about now. So let's remember, if we have a matrix A, let's let this be an M by N matrix. Well, and then if we have, let's say X, let's let this be an N by 1 vector, then we can realize A as a function or a transformation when we multiply on the left, right? So A, you say A acts on X by multiplication on the left, or you say the transformation of the vector X is induced by multiplication on the left by A, right? And so we have AX, and this equaled some vector B, where B was, well, it'll end up being an, M by 1 vector, right? And what we were thinking about, sorry, couldn't see. What we were thinking about in this new setting, or what we want to think about in this new setting, is thinking about A as a map or a function that takes, so A here is going to take a vector X and transform it into some other vector B, right? And so in coordinates we had, you know, A, well, I don't need coordinates for A with how I've set it up, but if we had like X equals X1 through Xn, and then B equals B1 through Bm, right? Then we were thinking about A as a function that takes vectors in n-dimensional Euclidean space, and it transforms them into vectors in m-dimensional Euclidean space, right? And so this is what we're going to be exploring more in depth now, is kind of viewing a matrix as how it's transforming a family of vectors or a collection of vectors into another collection of vectors, right? So just for example, like this may seem pretty abstract at the moment, but let's look at an explicit example. Let's let M equals N equals 2. And let's let A be the matrix 1, 0, 1, 1, right? Well, then we're thinking about if M and N are both 2, then A is really kind of transforming vectors in R2 to vectors in R2, right? In this prescribed way. So let's look at what happens if X is, let's see, what example did I use? 1, 2. If X is 1, 2, then let's see how A transforms this vector 1, 2. Well, transforms it by AX, which is equal to 1, 0, 1, 1, 1 times X, which is 1, 2, which the vector we get here then would be, looks like we're going to get 3, 2, right? And so what this map or this matrix A representing a map has done geometrically is, okay, well, we started in R2 and we had the vector 1, 2, right? So here's X. And then A, so if we want the XY plane here, what A has done is it's transformed that into the vector 3, 2. So 1, 2, 3, 1, 2, like this. And this would be B in the notation that I've described or that I've used previously, right? And then if you think about doing this to every vector in R2, you can see what's happening is it's taking every vector in R2 and it's transforming it and kind of like flattening and extending, right? And so that's a transformation, right? If you think about all vectors, or think about a vector field, right? If you've taken Calc 3 or DiffEq, you're very familiar with or traumatized by vector fields, right? And so if you have like a, let's say we had the vector field f of x equals, well, it'd be f of xy, right, equals 1, 2, where just every vector is the vector x here, right? Well, then what a linear transformation would be doing is if you think about the xy plane and then you think about a vector field as something that you kind of lay on top of the xy plane, well, then the transformation A is kind of pressing that, you know, it's kind of pressing it towards the x-axis and then stretching. So you can imagine kind of the entire vector field laid on top of this xy plane being like transformed, right? It's being rotated and then stretched or compressed based on the matrix. And that's exactly why we call it a transformation here. So let's do another example here. Let's say A is the matrix 1, 2, 2, 1, 0, 0. So if A is to be understood as representing a map from some dimensional Euclidean space to another dimensional Euclidean space, I would like to ask, so this is going to be a map from Rn to Rm, right? And so what I would like to ask is, what is N in this case, and what is M in this case, right? Or using the language that I've previously introduced, this question more rigorously asked could be, what are the dimensions of the domain and codomain, right? Because the domain, remember, is the source, right? It's the vectors that are going to be transformed. And the codomain is the target. These are the vectors that, or the entire space of where the transformed vectors live, right? Because remember, the codomain doesn't necessarily have to be the image, right? The image is the set of all transformed vectors, but the codomain could have, what I'm saying is the image could be a subset of the codomain. It doesn't necessarily need to be the entire codomain. So how would we find this? Well, what do we need to do, right? To find these dimensions, we need to understand A as kind of an action, right? It's something that we apply to a vector to transform it. Well, and if we have the vector, if we have the matrix A, which is 1, 2, 0, 2, 1, 0, and we wanted to multiply this by some vector x and then get some vector b, we have to ask ourselves, what are the dimensions of the vector have to be, right? Well, and then you think about, well, I need to multiply A by X. So what I would be doing is I would be taking the dot product of this vector with the rows of A, right? And to do that, the length of the rows has to be the same as the length of the vector X. And so therefore, X needs to be three-dimensional, right? because when I do matrix multiplication there, I have to have 3 elements or 3 components of this vector. And then therefore, we have x, y, z here, which means n is 3. And so what is the result here? Well, then let's compute this product. We're going to get x plus 2y for the first entry, and then 2x plus y for the second entry. And then we look at the dimension of the result here, right? This is a 3 by 1 vector, which implies that n is 3. Now this is a 2 by 1 vector, which implies that m is 2. And so what we have here, A, is a matrix representing a map from R3 to R2. So A was really a map from R3 to R2. Cool. So now that we have these examples and kind of a better intuition, I'm going to confess something. I've been abusing notation here. So to say that A is a function from Rm to Rn, this is an abuse of notation, meaning, it's not really, it can be understood, but it may not be like mathematically rigorous, right? Because a matrix is a matrix. It's not a function until you multiply a vector on the left, right? And so to say A is a function here is kind of odd. Like a matrix is a matrix, right? But there is a transformation that is induced by a matrix. And so for that reason, I want to fix this abusive notation. So let's denote. So here's some notation. We'll say T sub A of X from Rm to N, to Rm is the transformation given by T sub A of X equals A of X, right? And so I'll use this new notation. And I'll even shorthand this a little bit because it will be understood when we write it out explicitly. This will be understood. So really what I'll say is like T is a transformation given, induced, whatever, given by, or let's say with, is a transformation with matrix A, right? And so when I say that, it will be understood that T of X is defined as multiplying the vector X on the left by A here. Okay, and so now what does it mean to be a linear transformation, right? We've just been discussing transformations in general. Linear transformations are a subset of transformations. So a transformation from Rm to Rn, well, sorry, that's backwards. I've been using Rn to Rm is a linear transformation if for every scalar k and l in R, so these are scalars, and for every vector in the domain, so x1 and x2 in Rn, we have the following property. We have that T of k x1 plus L x2 is equal to k T x1 plus L T x2. Okay. So this is called the linearity property. If a transformation satisfies this property, then it is called a linear transformation. Okay, so this is a very important type of transformation, and we're going to see why it's so important in the context of matrices. So first, let's do an example, or let's see how to prove that a transformation is linear. So I have a claim. So this is an example, right? Claim. T from R3 to R2 defined by T of XYZ equals X plus Y, X minus Z is, and I'll just say is linear, right? Because it's understood that it's a transformation. So let's just say my claim is that this is linear. Okay. Now, how do we prove that? Well, to prove that, we need to show this property, right? If we can show that this holds for the specific transformation, well, then we can show that this is linear, or that would show that it's linear. So what do we need? We need two vectors. Let's say x1 is x1, y1, z1, and x2 is the vector x2, y2, z2, right? Because we need those two vectors, and then we also need coefficients, scalars, whatever, k and l. Cool. So let's let those vectors be as follows, and then we'll let k and l be scalars. Now, what do we need to do? Well, we need to look at the transformation of kx1 plus lx2. And what is this? Well, that's going to be, we need to understand what the inside, like what this vector is on the inside, right? Because right now it's a sum of scaled vectors. But in the definition of a linear transformation, we just have one vector, not a scaled vector, not a sum of vectors, etc. So what we need to do is simplify the inside here. So we have k times x1, y1, z1 plus l times x2, y2, z2. Then I'll do this in one step, but we can scale, right? We can pass the scalar multiple to the inside of the vectors, and then we can do the vector addition and get one vector that is k x1 plus l x2, k y1 plus l y2, and then k z1 plus l z2. Right? Now we have one vector that we understand how this transformation works. So how does this transformation work? It takes x, y, z, and the result is x plus y, x minus z. So the result here is going to be, well, we'll have x plus y, right? And so we're going to have this whole thing is x, and this whole thing is y. So we're going to get k x1 plus k y1, and then, sorry, plus lx2, my bad. And then plus y, which is the second piece, which is k y1 plus l y2. And then we have x minus z. So we have k x1 plus l x2. That's the first component, minus the third component, which is k z1 plus l z2, right? That's the result of our transformation here. What can we do from here? Well, from here, we could combine everything that has a multiple of k and everything that has a multiple of l. So we could write this as k, and then x1 plus y1 plus l x2 plus y2. Then on the second component, we'll have k x1 minus z1 plus l excuse me, L x2 minus z2, right? Well, and then we can split this vector up. We can split it up over the sum and then pull out the constant. So we're going to get k x1 plus y1, x1 minus z1, and then plus L x2 plus y2, x2 minus z2. And you'll notice after this simplification, that is precisely kt x1 plus lt x2. And so we've shown the linearity property here. Okay. So what I'm going to do from here is in the next video, we'll look at some important theorems and properties of linear transformations.